Okay, so maybe we'll just get started and people will start coming in. Hi, everyone. Good afternoon. I'm Arvindan Vijayaraghavan, and welcome to the second session of the Recent Directions in Machine Learning workshop at Fox. This workshop is being co-organized by Alexander Madry, Daniel Shu, and myself. So our first speaker in the session is Anima Anandkumar. She is the Bren Professor of Computing at Caltech, California Institute of Technology. She's also the Director of Machine Learning at NVIDIA, where she's leading the research group that develops next generation AI algorithms. At Caltech, she is also the co-director of the Dolcet Center, and she co-leads the AI for Science initiative. Anima has done a lot of really nice work on the foundations of machine learning, particular unsupervised learning, tensor methods, deep learning, and non-convex optimization. For her work, she is a recipient of several awards, such as the Alfred P. Sloan Fellowship, the NSF Career Award, faculty fellowships from Microsoft, Google, Adobe, various Young Investigator Awards, and she's also been featured as in the Women in AI by VentureBeat and several other select groups. Recently, she has been using deep neural networks to solve challenging scientific problems involving partial differential equations that arise in various areas of science and engineering. And she's going to tell us about some of her exciting work in this space. Yeah, take it away, Anima.
Thank you, Arvindan, and I'm really happy to see the theme of this workshop. I think there is a lot of intersections between machine learning and CS theory, and over the years we've talked about it. And when I was working on tensor methods, indeed there was also a lot of interest there, and of course with Daniel and Sham together. There was a lot of, I think, connections between what we think in machine learning versus CS theory. So with that, I think, it's only natural that we should have even more of this conversation. So yeah, with that, I think, what I want to talk to you about is this aspect of how we can frame operator learning as, learning in infinite dimensions, like going from a finite dimensional spaces to now infinite dimensions. How can we guarantee models that are universal approximators? How can we make them practical? And ultimately, how do we use them to scale up solving very challenging partial differential equation and other multi-scale phenomena. So yeah, the broad theme here that I want to start with is, there is a huge promise for using machine learning in scientific computing, right? And it's almost a necessity, because if we think about our current methods that use numerical solvers, right? There is a big gap between the computing available today and the nature of problems we want to solve. For instance, to me, the two canonical cases that we are in fact closely working on is, one is weather models and ultimately climate models. The challenge here is, of course, first you want very fine scale predictions, ideally all across the globe, and you also want to be able to do that much further into time, right? So if we are thinking about climate change, it would be over the next several decades. And so how do we maintain the right uncertainty and the physical validity while also being fast? So with the current methods, there's in fact like experts have computed that you would need 10 to the 11 more compute than what is available today in order to get to like a fine scale about 1 kilometer resolution over the next decade. So, and similarly, the other example is drug discovery and more generally, molecular level understanding. And in this case as well, if we want to look into engineering new proteins, we want to discover new drugs, the space is so vast. And so just the aspect of using GPUs, using supercomputers, all that can help you, but it's not enough, right? And that's why machine learning is necessary to be able to tackle some of the hard challenges. And you can, of course, frame this in terms of, right, in fact, partial differential equations in the case of weather and climate models. They're primarily based on fluid dynamics, very fine resolution, these, right, like LES models, essentially the eddy simulations. And you could even go further into like microphysics and look at precipitation, and that would be even more expensive. But ultimately, these are partial differential equations. And similarly, if you want to look into molecular property, some of the classical mechanics is not good enough, right? I mean, yes, you can get like a broad picture of like the dynamics of molecules, but if you want to predict carefully the binding and these properties, you have to go down to quantum mechanical level calculations. And there, we know there is this Schrodinger's equation that governs all particles, but then computing it exactly is infeasible. I think there's a back of the envelope calculation that even to do that on a 100-atom molecule would take more than the age of the universe, given the current supercomputers. So that's, these are really exponentially scaling computations. So then the questions is, what are reasonable approximations to make? And how can machine learning maybe learn those approximations more automatically, right? And then the question is, why not use the current machine learning methods? What is the need to develop better methods? If you look at standard machine learning, there's a lot of limitations. The primary one being the generalization capabilities, right? So in terms of like the climate models, we want to predict climate for the next century that is unprecedented. So the past data is giving some guidance, but there's also distributional shifts. So how do we enable this kind of extrapolation? And for that, you need to incorporate the physics, right? So that's the only way you can, make sure it's valid, and we can also have the right uncertainty estimates. Similarly, in the case of like Schrodinger's equation, you can also ask, what are the constraints I want to incorporate here? There is the 3D rotational symmetry, right? Or so you want to build that equivariance into the models. We can also look at features given by molecular orbitals that I'll show later. So all these additional aspects of the domain are important. And we want to ask how we can bring all this together to enable this zero-shot generalization. So going beyond the standard supervised learning to regimes where we would have significant shifts in distribution from training data. And in fact, in the case of the drug molecules or any other, right, molecular property prediction, we cannot generate training data, right, because it's very expensive. I told you the exponential scaling. So with traditional methods, we may be able to get only limited data of small size. You want to then use that and directly predict on very large molecules. So how do we ensure validity, given that these are very challenging extrapolation tasks? And so that's why we need to be careful in designing machine learning methods for these challenging cases. But of course, there's a lot of promise with the use of AI. And one important aspect is once we incorporate these AI and machine learning methods, we can hope to avoid the fine scale discretization needed for traditional numerical methods, right? So if I'm solving fluid dynamics, it is multi-scale. So numerical methods have to go to the finer scale and right, iterate over that in order to get high fidelity solutions. If you do that at the core scale, you will just go completely wrong. And so that means they require also very high precision. So you usually have like 64-bit floating point in the traditional high performance computers. But with the use of machine learning, one is we hope be able to take bigger jumps. We hopefully do not need to resort to very fine scale stepping both in space and time to solve these PDEs. And that's because we hopefully will learn good representations that will help us, right, like kind of take these bigger jumps while we iterate and get to the solution. And so that will give us a big speed up, as you'll see in our experiments. We've noticed that. And the other important aspect is we can also do that hopefully with much lower precision. In fact, a lot of deep learning, we are seeing precision also go down. We are down to 16 bits or even sometimes 8 bits. There's even models with just 1 bit, right, representation. And so that's the additional benefit we'll get by enabling this as machine learning workloads on supercomputers. So there is like going to be a big gap between whether you learn it as a machine learning workload versus a traditional HPC workload. And so these are aspects, I think, that'll help us scale up these methods even better on real systems. Yeah, so let me now get into solving partial differential equations. Right, so the one thing I want to first differentiate is between solving one instance of the problem to learning a solver for an entire family of PDEs. Right, so in solving for one instance, we're already given initial and boundary conditions, right? This is standard for input into a solver. And then we want to predict what is the solution at every query point. So we'll have query points and we can predict solutions. And so this one, you can also use a neural network to solve an instance of the PDE by directly optimizing on the losses given by the equations. And this is what the physics-informed neural network does. But to me, this is not learning because we are merely using neural network as an optimizer. Right. On the other hand, learning system would be one that learns the underlying solution operator. So, given, and this is data driven, so we can have multiple data points of showing the mapping between inputs and boundary conditions to the solutions. And note that this could be a different discretization or different grids. Right, but I should be able to then have test points at a different resolution and still be able to answer this. So that's because we are learning the operator in the function space. So from the entire input domain to the solution domain, we are learning the mapping. And this is potentially an infinite dimensional space. And the question is, once we've learned the solution operator, then we can provide a solution at any discretization. And so that's why this method would be a resolution invariant or a mesh invariant system, because it does not expect your query points to be in a specific resolution or grid. And so that's the main difference with respect to just using standard neural networks, because they're designed to map in finite dimensions, fixed dimensions, right? So you have all your whether it is vision transformers or convolutional networks, resolution of the input is fixed, you train in that resolution, test in that resolution, right? And typically, if you try to change the resolution, there is usually a big drop in performance in the standard models. And that's why, to me, they are not suited for the use as a partial differential equation solver, because we expect the flexibility. If you ask practitioners, they may want to kind of have the flexibility to change the grid. Like if it's an airfoil, you would, with this very complex geometry, you would have one kind of a grid versus say this shape here. So you will, you can change the grid, you can change the resolution. You want to have that flexibility. So is there a method that we can design that has these properties? Right. So, and that's why we call this a neural operator, because it's learning this operator that maps between these continuous domains rather than rather a continuous function between these domains, rather than just a finite dimensional space. So how do we go about doing this? As with everything, we should start with simple examples, right? And in this case, the simple example is, thinking about linear operators. For instance, you can think about linear partial differential equations, such as, these are second order elliptic PDEs, right? And if you want to ask what is the solution, we know that the inverse of linear differential operators can be written as integral operators. So you can express the solution as integrating with respect to a kernel. And so this is a convolution. In fact, this could be a global convolution depending on the nature of this kernel. And with this, we can obtain the solution at all points. So you can evaluate this at any point in the domain. It's not fixed to one resolution or grid. So this we know is the solution operator if it's a linear system. And this example here is the heat diffusion equation. This is perhaps the most common differential equation, right? A partial differential equation that you maybe have seen. And so in this case, the kernel is in fact even simple, right? Like you can see this would be the nature of the kernel, and then you would integrate over this. So this is something we see in the PDE 101. And so this holds only for linear systems. But then what we want to ask is, if this is the case with linear differential operator, we can do this as one shot, as finding it through integration or convolution. For a general system that is potentially nonlinear, what if we stack several layers of that, right, and compose with nonlinearity? And in fact, this is also present in some of the traditional solvers. They are iterative solvers, so they iteratively refine the solution. They tend to be linear, but that's not necessary, right? You could even make that non-linear. And so this now starts to look very similar to now stacking up many layers of this. And so that's how we came up with this principle that, if each layer of this neural network, right, like learns an integral operator, right, and then we can compose it with nonlinearity, overall we can get to an expressive model that is also approximating solutions of general nonlinear PDEs. And yeah, so that's quite, I think, simple and intuitive. So that's our proposal for having a neural operator. And the idea is, if like these layers doing these convolution or integral operator, they can be linear, right? But they are in general non-local. So they give you the ability to capture global dependencies, which we'll see in a minute is important if you want to capture, say, like fluid dynamics. That's not just localized, there's global dependencies. And then adding nonlinearity means we are not just limited to the solutions of linear operators, but we can also capture nonlinear operators. So one additional detail is, right, we could also do this in a lifted space, and that could give us better representation. And this is something in practice we see helps quite a bit because when we look at PDEs, right, each point is usually low dimensional, right? Like we're thinking of 2 dimensions or 3 dimensions since they are physical systems. Of course, you could also look at the quantum case, and there it's high dimensional. But for this part of the work, we looked at just the physical PDEs, like fluid dynamics. And so there, because our inputs lie in low dimensional physical spaces, it's better to lift to a higher dimensional channel space and then learn the operator in that space to get us, again, better expressivity. Again, this is a detail, but helps in practice. So yeah, to summarize, the way we designed this was to essentially mimic the neural networks in finite dimensions, where there is usually a linear function followed by nonlinearity. And in finite dimensions, the linear function is typically, right, matrix multiplication if you have, right, the MLP, or its convolution is also linear. So we are composing these linear functions with nonlinearities to get a universal approximator. And so we can also now see the same with learning in infinite dimensions. So learning an operator, you can do the same as long as we have a layer that can learn a linear operator. We can compose it with nonlinearity and get universal approximator for any continuous operator. And so with this design, right, like you can now see it's not limited to one grid or resolution, because now I could have query points with, specifying these conditions. I can, do that at any point in the domain, and I should be able to get the solution once the model is trained. And so that's the idea that, we can build this on the foundation of the integral operators, which are the solutions for linear differential operators. So given this, of course, then the next question is, how do we practically solve this, right? What should the layer be? How would we compute this convolution operation efficiently in practical systems? So before we get to that, I guess one, like what I mentioned, the universal approximator, we can establish that. So, and as in finite dimensions, even here, you can see that just 2 layers of it is enough, right? Which, because all you need is some nonlinearity, and you can have a universal approximation. And also, for specific families, sorry about this typo, like Navier-Stokes, which is fluid dynamics, right? So we already know a lot about the structure of the solution operator and how, right, it is finite dimensional. And so those the dimension of the solution operator can also then help us determine what is the approximation error bound, right? Like what should be the size of my network to reduce the approximation error. And so we can be more precise for such parametric families. So as I said, the next question then is to ask, how would we solve this convolution and do that efficiently? So we again take inspiration from numerical methods, like when we are thinking of this graph neural operator or multipole graph neural operator, right? So the multipole is essentially like mimicking the multigrid method, but now learning these kernels, right? And we can also stack this over several layers to get good expressivity. So the idea is we can, the input, we can like have an arbitrary discretization, we can form a graph over that. Again, we need to decide how we construct this graph. What is, the set of neighbors, how do we determine? And once we've done that, we can use that to approximate the kernel. And same with the multipole method, you can do this now at multiple levels, because if you try to do the graph, especially for systems such as fluid dynamics that have global dependencies, the graph becomes too dense and it's too expensive to compute this. So we can do the multi-level graphs, right, which is essentially the multi-grid method, and that can reduce the resources needed for computing this. And we could also do like a PCA, like some low rank approximations, and learn that in lower dimensions. But it turns out, compared to all this, the one that has been successful practically a lot is doing this in the Fourier domain. And there are several reasons why that turned out to be the most effective. And one thing is, first of all, it makes computation very fast, right? Because all we need to do is solve for FFT, we have the fast Fourier transform, and we learn the weights in the Fourier domain. So learning the weights in the Fourier domain, and we just need element-wise multiplication. So this is very fast. So we don't have to worry about explicitly solving this convolution. And the other reason is the Fourier domain captures global dependencies very well compared to if you were having convolutional neural networks with local filter that has a small receptive field. I mean, that's also the reason why transformers have been much more effective, right? And in fact, we show transformers as a special finite dimensional case of neural operator. And we show how to, also incorporate these kind of Fourier layers there to make them more effective, which is a recent ITERATIVE acceptance. If I have time, I can discuss that, but leaving that aside, the main idea here is the Fourier domain captures these global spatiotemporal relationships much better than some local filters. And then the other reason is also that in many of these cases, it's also a nice inductive bias, right? Even numerical methods tend to do some of these computations in the frequency domain because we have a representation that is much more effective in capturing the multi-scale phenomena. And so with all this put together, that's where we have a layer that computes these convolution operation through the Fourier transform. We learn the weights in the frequency domain. And when taking the inverse Fourier transform as a regularization, we keep only low frequency modes. I mean, of course, if it didn't have the nonlinearity, this would not be very expressive. But because we have the nonlinearity, this is like a balance, right? How much regularization do I do? And with this, there is also more robustness because we only keep the low frequencies, and also more resolution invariance because we're only like irrespective of what the input resolution is, the processing here in each layer only keeps low resolution. I mean, sorry, low frequencies. So which is related to resolution. And we also add another bias term here because sometimes it's easier to capture some of the fine scale discontinuities like edges much better with this skip connection. So we can do this kind of, again, architecture design depending on the use case. So that's the overall framework of Fourier neural operator. And now we've seen good gains in many domains. So I'll take a few minutes to show that. And the first thing we did was these are two-dimensional Navier-Stokes equations. And here you see we can train on just coarse resolution data, right? The training time, it's only seen this coarse resolution data, and we can directly evaluate it on fine resolution. And still, visually we see it works well, but also we see that with the frequency spectrum here. So here, this is the wave numbers that are in training because it's lower resolution. And these are the higher resolution information. And you see that it has captured it better, especially compared to the traditional neural networks like UNets. And the other benefit is what we've seen is, in this case, it's 1,000 times faster than traditional solvers. In fact, these numerical methods for this setting is well developed because you can do a pseudospectral solver, you can do that on the GPU. So it's a very much apples to apples comparison, and still we are much faster. And that's because these numerical methods still need to do fine scale discretization and step over that iteratively to get high fidelity solution. Whereas in the case of the neural operator, once we've learned these frequency domain mixing with nonlinearities, right, it's very fast to do inference on them.
Anima, just a quick question for clarification. Yeah. So the input here, is it for the neural operator, it is boundary conditions, is it? Or
initial and boundary conditions together.
Initial and boundary conditions together. I see.
As you would specify for any a PDE solver.
Okay, thank you.
Yeah, And in this case, the boundary conditions are periodic. This is kind of the starting case, right? Like the warm-up case that people use to test this. And since then, we've done many other cases.
I have a follow-up question. So in terms of learning, so this is the input to solving the PDEs, I guess, right? The boundary condition. But in terms of learning, what is the input for this neural operator?
The input is this training data. So we would have the initial and boundary condition and the solution from an existing solver.
And you know what the solution looks like, I guess.
Yeah. So this is supervised learning, right? So we also have a framework where if you don't have the supervision, what to do, can we use the loss from the equation themselves? In a bit, I'll talk about, but here it's fully supervised.
And so you see these frames here, which are on the top of your slide, the 3 frames. So these are the supervised learning examples that you feed into these neural operators. And it outputs something like the 2 bottom figures.
These are like training data, right? And whereas we're testing it on a different resolution, right? So we would be then giving initial and boundary conditions at this now higher resolution, and it still can output the solution in that case.
Okay.
And so that's where, like if we ask to do this in standard neural networks, it would fail quite badly. You could even try to do simple interpolation on top and it would not work very well because, right, it fails to capture the fine scale phenomena well. And we also know like these standard neural networks like convolutional nets have a bias towards low frequencies, right, which is a big problem for systems such as these that have lots of high frequency content.
Thank you.
Yeah, so that's what we see in this example. We also compared it with many other learning methods, right? So these, the other learning methods that are only limited to the same resolution. And even that we have better errors. So the idea is, even if you don't need to do super resolution, the aspect of trying to learn it in a resolution-free manner can also help us learn a system with better error. So that's the idea, that it can generalize well across different systems. Yeah, so far I assume that this supervision is available, but many times maybe it's very expensive to get, so you may have a few examples, right? And so far we didn't take into account the equation loss at all. So it's very natural to also add this, right? Whereas I mentioned in the physics-informed neural networks, what people do is to just use one instance of the equations and use the neural network as an optimizer to solve them without any learning. But now it's natural to bring the two together. We can also incorporate the loss from the equations and any other conservation or physical constraints we may have, along with any data we may have from existing solvers. And so the idea is we can train with this joint loss, but we can also do better, right? Like at test time with the current solver, we are just treating it as a learning system where you learn and then you infer, right? Without changing anything about the system. Whereas even at test time, we know the equation, right? I'm giving you now a new instance with new initial condition, boundary condition. I still have the equation. So I can easily validate if my solution is correct or not. And so that's different from a standard machine learning problem. In the standard machine learning problem, if at test time, I'm asked to classify it's a cat or a dog, I have no idea knowing whether I got the correct answer or not. Whereas here, once I have a proposal for a solution, I can easily verify by plugging in the equations. And so it's natural to also fine tune that and to ask, can you further reduce the loss as we go through the equations? And so that was what we see with this framework that, if you now want to be good on this specific instance, you can further fine tune it. It's also natural. We could add meta learning to this. We didn't currently. So we can bring in all these other aspects of machine learning beyond supervised learning to make it even better here. And in this case, what we see is incorporating physical constraints make it easier to go from one Reynolds number to another much more effectively. So transfer learning is more effective if we have the physical priors, which is very natural. And the other is we can do with much more limited training data, just 400 examples from an existing solver, but lots of data augmentation, because I can always augment data with just the equations without having the solution from an existing solver. And that'll improve generalization. So these kind of data augmentation, right, which we've seen in computer vision, we can also do that here because we have the equation laws, it's natural to do that. So we can also think about doing inverse problems in a much more natural or direct way. Because so many applications of PDE systems involve, once you have the forward solver, right, to try to propose what is the inverse of a solution. And because it's single post, people do MCMC and do it over lots of iterations to get the answer. So in this case, if we want, one proposal of what the inverse would be, we could directly learn the mapping in a backward way. That is from the solution to the initial condition. And so by training this on several examples, we see that it also, because at inference time, this will be very fast because it'll be just one pass through the neural network as opposed to doing MCMC. So this also leads to a significant speed up. And so it's still an open challenge on how we could get the right uncertainties, right? Because many times people in inverse problems not only care about a valid solution, but also its uncertainty. So this directly doesn't give us. So the question is, are there ways to incorporate that? And that's, to me, I think it's possible to do that, but we haven't yet addressed it yet. Yeah, so far I talked about, right, like kind of predicting, say, fluid dynamics over a fixed time horizon, having enough either data or equation constraints, and hopefully learning a good solution. But we know many of these systems are inherently chaotic, right? So meaning at some point, no matter what you do, you're going to diverge because small changes will completely change the trajectories. But we do know many of these systems still have attractors, right? So over a long horizon, you will have statistics that converge, even though individual trajectories may not. So now we want to change the narrative as, instead of trying to accurately predict a trajectory, which is ill-posed over a long horizon, can we instead learn a model that simulates the long-term behavior, right? That has the right set of attractors. And so for this, what we want to do is rethink the way we look at learning any kind of temporal data, right? So what we usually do in standard new deep learning is to take the entire trajectory, fit your model to the trajectory, like say a recurrent neural network. But instead with these systems, what we do know is it's Markovian. So as long as you can capture the local evolution effectively, at test time, you just need to compose, right? So you don't need to train over a long horizon. In fact, training over long horizons can make it unstable. We've seen that with recurrent networks. In practice, they become very unstable even on a reasonable horizon, and people do all kinds of tricks to avoid that gradient explosion or vanishing. But in this case, we won't have that issue because we'll only learn short-term statistics of this. In fact, like an infinitesimal transition, right? That we want to learn how it has this change in behavior over a short time scale. And then at test time, if we compose it, we will get the attractors. And so we see that this kind of training also ends up predicting the trajectories much longer than LSTM or all these recurrent neural networks, right? Because one is it's more stable, so it can hold up longer. And the other is capturing these different statistics. Here it is energy. Sorry, there is, I think, a typo here. One is, I think vorticity, if I'm not mistaken. Density. So all these different properties, we can also aim to predict them and get these statistics well. And ultimately, we can use that to simulate these chaotic systems. We can ask what are the attractors here and how well does it capture the attractors. And so just a teeny visualization of the aspect that it can capture these phenomena reasonably well. So I know we are running out of time. Just a quick, I think because I mentioned it earlier, we can think of transformers as a finite dimensional approximation of neural operator and vice versa, right? So we can ask now, how do we make transformers also better generalizable and more resistant to any, right? Like kind of, even if we change the resolution, can they perform well? And so what we can do is the attention mechanism, we can replace it with these Fourier neural operator layer. And so the main idea is like transformers are doing spatial mixing, and we can now think of that as integration if we do it as continuous generalization. And we can then solve it through the Fourier transform. And there's some details of a good architecture design to make this scalable or natural images. And what we do see is, compared to vision transformers, we have similar quality images, right? But much better in terms of the speed because Fourier transform is blazingly fast. So I think this is a promising direction to make self-attention more efficient, but also more scalable. And compared to some of the others that also make self-attention efficient, these tend to have better representation abilities. So I think that's an interesting aspect as well as a connection. So I know I'm out of time here, so I'll stop. I mean, there are some other applications we have. I encourage you to go check out the slides. There is more details there. There is also like weather and climate scenarios we've been looking into, like looking at carbon dioxide storage, looking into how the replication in coronavirus happens, and can we predict the molecular dynamics that comes out of that, right? So these were like Gordon Bell special prize finalists. So I think there's a lot of these aspects we can incorporate into different workflows using this. And also symmetries and aspects for molecules as well is effective. So we've incorporated that and gotten really good speed ups compared to standard quantum chemistry methods. And that was also part of this Gordon Bell special prize. So I will stop here and happy to take questions if there's time.
We have time for a few questions if there are any. Yeah, so please feel free to unmute yourself and ask your questions. Maybe let me get it started. Let me start out with the question. I was just curious. So with chaotic systems, what are some of the challenges that come up? Is it in stitching together these different neural operators that you learn for different, like windows of time or something? Or like,
yes.
I guess what are the,
Right. So I think in a real world that can happen, right? Because there's just drifts. Right now in these, right, like kind of artificial systems, we know, for instance, the oscillator system or Navier-Stokes, right? Like we are not assuming, right, like parameters changing over time, because in that case, we would need to also track if there's a distributional shift, and then we need to stitch over time. But in these idealized systems, we only need to learn once, right? Like the short-term behavior. And then we can directly just compose them. I mean, one challenge that we are still like right now working on is, right, I mean, it's not always guaranteed to be stable, right? Because if it misses part of the space in the short-term learning, like learning the short-term behavior, it could explode. And so we are finding ways to dampen it so that it doesn't happen, and then learn better that part of the space. So we are capturing over time the full statistics and all the attractors. And so that's, I think, will make it much more useful, because that way, even in chaotic systems, we have now this learning that is going to be stable, right? So we can learn the behavior of this. And of course, if we then want to bring it to more real world scenarios, we would have to continuously monitor if like these statistics are changing over time. And it's an open problem on how to piece them together. But yeah, that's an interesting question.
Are there other questions? Okay, so maybe let me ask one more question. I was just wondering if there are there like theoretical questions or maybe algorithmic questions that you think are somewhat specific to dealing with neural operators that you think are good opportunities to develop theory or try to understand?
Absolutely. I think, like the approximation error that I mentioned, right? Like aspects of how to make that for different classes of operators and relate them to what we know, right, in terms of like different families of PDEs. I think that's still open, but I think the more interesting one that is still unaddressed is, right, like generalization abilities, right? Like how, in these systems, we know more about the multi-scale nature. So how do we use that, and are there better inductive bias, right, to encourage generalization here, and this interplay between approximation and generalization, which all is present in finite dimensions. But here, the thing is, there's so much of decades of research into these systems, right? And more of an understanding of that behavior. So that, to me, like serves as a good test bed for, saying if this is the theory of deep learning, does it hold here? Well, for instance, this multi-scale learning, how does it do in systems where we know there is multi-scale behavior? So I think those are also interesting, and we barely scratched the surface. And when it comes to more of using, like, there is very little supervision, right? How do we incorporate like these equation losses, or whether there are other symmetries in the system? We know, like, if we just did equations, the landscape of optimization is really hard. Right? And it's not just a limitation of expressivity. Even if you had a very large network, sometimes you get stuck. So that brings back also the optimization questions, because in standard deep learning, we've found like, no, you just over parameterize, and you have a system large enough, right? You can get away with these optimization issues. But here, many of the systems we're going to deal with are going to be massive, right? We can't keep growing this to very large networks. It can't be in the over parameterized regime. So I think all those problems become more relevant here.
Yeah. Any other questions for Anima? Okay, if not, let's thank the speaker again. So Elias, are you here on the Zoom call? Oh, thank you.